Okay. The next thing to discuss is a bypass stream. Okay, as you can see this in this slide. Okay, this stream is bypass stream because it doesn't go to this unit process. It will bypass it. Okay, and it's basically because we want to control the composition and the property of a product. Okay, and it's just a fraction, not all. Okay, not everything, it's just a fraction. Some will goes into this unit and some will just bypass it. Okay, so why we need a bypass stream? Because we want to control the composition of a product. Okay, and then because of the property of the product, and because of the composition, because we want to vary the composition of the product. Okay, it's okay. It's just a simple, just to let you know that there are this process occur in a real industry. Okay, when you have a multiple unit process, maybe some of the stream might be bypassed and then bypass some of the unit process. And when you do a recycle, I believe you already watched the previous video about recycle with reaction and without a reaction. For the recycle with a reaction, you have to take care about the conversion, whether it is overall conversion or single pass conversion. And then for the without a reaction one, you have to take care maybe about the phases. Yep. And it's let us continue with another topic. Okay, maybe a last topic for this multiple unit, which is recycle and purging and purge. Okay, what does it mean by purge? Purging meaning to say we remove some of the from a recycle stream. We remove some of the some mesh, some fraction of mesh we have to remove in order to avoid accumulation of the some component, because we keep on recycling. We want to avoid the accumulation of certain chemical in our process. That's why we need to remove some of it. Okay, for example, when we have a reactor and then we have a feed to the reactor, at the same time, we do have a separation because we want to recycle back the unreacted reactant. Okay, this is adsorber. Adsorber is a one type of a separation unit. Okay, and when we do a recycle for a long time, there will be an accumulation of certain component, and we want to avoid this. Okay, so we're going to purge, meaning to say we want to remove some of it. Okay, in this yellow line, I believe you can see it. This is a purge stream. Okay, so for example, we have a fresh feed of this C2H4, oxygen and nitrogen. Okay, I'm sorry about the typo there, but and we have a recycle stream. Okay, different composition. Okay, and then we do some recycle and we have a product. Okay, some of the chemical being taken as a product, some of it being recycled, and from the recycle stream we want to avoid accumulation, so we purge some of it. Okay, we purge some of it, some amount, so that the C2H4 or maybe the nitrogen, which is the unreacted, the inert gas here. Okay, because this occur when you have a reaction with air, because air contain oxygen and nitrogen. So this nitrogen is not used in this system, in this process. Okay, and the amount of nitrogen will keep on increasing. So you need to remove, okay, you need to remove some nitrogen. You need to purge this nitrogen from the system. If not, the value of this nitrogen will keep on accumulate, will keep on increasing, and it is not good because it will disturb the rest of the composition, will disturb the balance of this system. Okay, so don't worry so much. Let us take a look on the example on how to calculate a recycle and purge. Okay. Okay, we have here recycle and purge in a synthesis of methanol. Okay, so to synthesis of methanol, you need to do a reaction of carbon dioxide and hydrogen to produce methanol and water. Okay, so the fresh feed, okay, the fresh feed, which is before a recycle, before mixing with a recycle stream, it contains hydrogen, carbon dioxide, and 0.4% of inert. It could be nitrogen and it could be another gas, and it's easier for us to put it as a inert. Okay, inert meaning to say it doesn't have anything to do with the reaction, it's just there. Okay, so the reactant, okay, we have a reactant. Of course, when we do a reaction, we need a reactor. The reactor effluent pass to a condenser. A condenser is another separation unit, okay, which is, it will do a condensation process. Okay, so the separation unit have a lot of name. It could be a condenser, it could be absorber, it could be a crystallizer, it could be a filter, anything that do a separation process. So this condenser remove all the methanol and water, and it doesn't remove the inert. Okay, and then the later substance are recycled back to the reactor to avoid build up. Okay, that is I'm talking about just now, to avoid build up, meaning to say we don't want after a long time of recycle the inert value is increasing in the system, and it will disturb the system. Okay, a purge stream is withdrawn. We need to do a purge stream. Okay, and then the information given, which is a composition of carbon dioxide, not the fresh feed. Okay, the feed to the reactor, not the fresh feed, meaning to say it's already mixed with the recycle stream. Later on, we check the block diagram. It has 17 mole of H2 and 2 mole of inert. Okay, and the question also mentioned about single pass conversion. Remember what is single pass conversion, where you can calculate it. It is a 60%. So you need to calculate a molar flow rate, molar composition of a fresh feed. Okay, we don't know the flow rate and the composition, and the total feed to the reactor. Okay, the total feed to the reactor and the recycle stream together with the purge stream for the 155 kilomole production of methanol. Okay, so this is the block diagram for this process. Okay, we have a reactor, we have a condenser here. So we have to put all the unknown. Okay, start with our fresh feed. Okay, we put it as N naught. Okay, and then the initial composition of carbon, okay, carbon dioxide, and the composition of hydrogen together with the composition of inert. Okay. The question only mentioned about the composition of inert. Okay. So for the composition of carbon dioxide, we put it as this one, and the remaining would be the composition of H2. Okay. And we take a basis here, okay, because we don't know the value, but we are given the composition of these three components. Okay, in the question you can check back. Okay, so we take a basis of 100 mole. Okay, and we don't know what are the mole of the reactant. Okay, mole of the product came out from the reactor, so we put it as N1, N2, N3, and N4, but the composition, the mole of inert have been mentioned in the question. Okay, and the composition of the one of the recycle stream, okay, and the composition of a product, okay, the composition of the purge stream, okay, as you can see here, this is same composition, okay, same composition, but here the value of N5 and N3 represent the mole is different, but the composition is the same. And the composition in the recycle stream, okay, it have again the same composition, okay, all these have the same composition, but it have different mole. Okay. Okay, again, what you need to do, okay, you need to do a boundary condition, and you have to do a degree of freedom analysis. Okay, so for the overall boundary condition, it have 0 degree of freedom. Later on, you can check by yourself this unknown. Okay, try it by yourself, this unknown. Okay, and then the boundary condition here at a mixing point, again do a degree of freedom. Okay, same goes when you have a boundary condition at a reactor, do a degree of freedom analysis together with a boundary condition at a condenser. Okay, do a degree of freedom analysis, okay, and you get 0 degree of freedom. Another degree of freedom, okay, you haven't seen this previously because last time you only consider here, but this time you also need to be considered here, whereby at a recycle and purge stream, okay, it's not a mixing, it is a split point between a recycle and a purge stream. Okay, and there is also a degree of freedom there. Okay, so you will need all these degree of freedom. Okay, I just show it by one because it's really complicated here if I put it together everything. Okay, so that's why I showed it to you one by one. But here you are quite lucky because you have a lot of 0 degree of freedom, meaning to say you can choose any 0 degree of freedom to start with. So I start with a reactor first. Okay. At a reactor, we have the information given 60% of a single pass conversion, meaning to say another 40% of the H2 it is came out from the reactor because it is unconverted or unreacted. So you can get the value of N2, okay, which is a mole of mole of hydrogen. You can get the value of mole of hydrogen came out from the reactor. Okay, and then you need to perform a hydrogen balance. And remember here, it is at a reactor, there are a reaction. So you need to have a complete equation of material balance, which is input plus generation equal to output plus consumption. Okay, so you have to calculate the consumption of hydrogen. Okay, because of this is a reaction, you have to calculate the consumption of hydrogen because later on this consumption of hydrogen will help you to determine the amount of carbon dioxide being consumed. Okay, so from 0.7%, 0.7 mole and 100 mole, which is the input, there is no generation, it is equal to 0. There is no new generation, new hydrogen being formed. Okay, you have only the input and the output you already calculate here, and the consumption you have to calculate the consumption of hydrogen. Okay, you get this value. Okay, with the information of how much the hydrogen being consumed, you can determine what is the consumption of carbon dioxide. Because from stoichiometry, 1 mole of carbon dioxide react with 3 mole of this one. Okay. 1 mole of carbon dioxide react with 3 mole of hydrogen. Okay, and you will have you can calculate how much the consumption of CO2. Okay, by using this one, or you can write it like this: 42 mole H2. You can write it in this way: 1 mole CO2 and 3 mole H2. So you can remove, so you get the amount of carbon dioxide consumed, because this information will be used here. Okay, so next you have to do a carbon dioxide balance. Okay, to balance a carbon dioxide, basically here 0.28 times 100 input. Okay, there is no generation of carbon dioxide, and the output, which is the N1, the output plus the consumption, which you can get from here. Okay, so you can get what is the value of N1. Okay, moving on, again from the information of how much how much of the hydrogen being consumed, we can determine how much the mole of methanol being produced. Therefore, 3 mole of hydrogen will generate 1 mole of methanol. Therefore, you can calculate the generation of methanol. Okay. And you can use this formula, this information to do a mass balance for methanol. Okay. There is input. Okay. So at this reactor, the methanol, it doesn't have an input because there is no methanol here. There is no input, but there are a generation from this process, which is 40 mole, is generated in from this reaction, and you have also N3, which is the output, and there is no consumption. Okay, because this consumption is applied for the reactant. This generation is for the product, unless you have another reaction. But here you have only one reaction. Okay, so I believe you already determine what is N1, N2, and N3. Okay, again at the reactor, you can determine the amount of H2 being produced. Again, from stoichiometry, 3 mole of hydrogen being produced. Being react will produce 1 mole of H2O. Okay, I'm sorry, this is a typo here. It should be H2O. Okay, so you can do a material balance for H2O, which is you will straight away get the value of N4. There is no input, also just the generation and the output. There is no consumption because it is a product. Okay, so from there we already determine what is N1, N2, N3, and N4. Okay, let's move to a condenser. When you have a condenser, the value of N3 and N4 already been determined, so here you need to determine this one. Okay, we start with a total mole balance. Okay, N1, N2, N3, the input equal to output. Okay, we get one equation. We get the value of N5 because N1, N2, N3, and 4 already determined previously. Okay. We can also do a carbon dioxide balance because we want to determine the value of X5C. Okay, so X1 is equal to this one because there is no carbon dioxide here, just here. So you can get the value of X5C to be this one. Same goes when you have a hydrogen balance. Okay, at a condenser, you can get the value of XH5, X5H. And the composition of inlet here, you can determine from this. Remember that all the composition will become, the summation of the composition is equal to 1. So you can determine is the composition of inlet in the recycle stream and the purge stream. The next one, you have to go to the recycle mixing point, okay, whereby you can get the value of N1, N0, and Nr, okay, whereby you do a total mole balance and an inert balance. From solving 1 and 2, you get the value of N0 and Nr. For the carbon dioxide balance, at the same mixing point, you will get another equation. You will get the value of this one. Okay? Don't get confused when I wrote it as here. It is N0 times X naught C plus Nr times Xc X5C, because this is the CO2 balance. Okay? And then the recycle the total balance at a recycle first splitting point. Okay? You already know what is Nr and N5. You can determine what is NP. Okay, because of we want to determine for 155 kilomole of methanol, meaning to say all these streams have to time with the coefficient. This question about the N3, the production of N3 for 155 kilomole. Okay. But the basis we set is 100 mole. In order to get this amount, each of these streams have to time with the scale-up coefficient. That's why here 155 divided by 40. So at each stream, when you have N1, Nr, N5, N1, N2, and all the streams have to time with 11.1 because we want to scale up. We want to get 155 because we set a basis of 1 kg, 1 mole with 1 mole of basis, we just can get 40 mole of C3, the methanol. But the actual, what we want to be 155 kilomole. So, what is the value here? Okay, to determine the value here, we have to time with this one. So, each of these streams have to be timed with 1.11.1 kilomole per hour. Okay, so I think that's all about this topic. Okay, I will see you in another topic. Okay, if you have any question, please let me know, and you can write it in a comment in your Google form. Thank you for your time.